now that we have some trigonometric limits, we can try to take the derivatives of trigonometric functions. So if I wanted to, I can try to find the derivative of sine of x. And since I know nothing about what it might look like, the only thing that I can do is apply the limit definition, right? Whenever there is nothing else that we can do, we go back to the definition. If there is anything else that we can do, we try to avoid going back to the definition unless it becomes necessary. So this is the limit as h goes to 0 of sine of x plus h minus sine of x all over h. Well, that's not pretty. But sine of x plus h, we know that we can do something with it. We know that we can expand it because we know how to find the expansion of sine of a plus b. There's nothing else that we can do. So since it's the only possible step, that seems like a pretty good step to take. So we take as our next line the limit as h goes to 0 of sine of x cos of h plus sine of h cos of x. And just because sine h and cos h are their own functions, you might want to put everything in brackets so it doesn't look quite as strange. And then we have minus sine of x, and the whole thing is divided by h. And notice we have sine of x over here and sine of x over here, so we probably want to collect these two terms. And we get the limit as h goes to 0 of sine of x times cos of h minus 1 all over h plus sine of h over h times cos of x. Put this in nice big brackets, and that's it. We know that this limit over here goes to 0. We know that this limit over here goes to 1. And so when we take the limit as h goes to 0, we have 0 times sine of x plus 1 times cos of x. And so the derivative of sine is simply cosine of x. If we have that, we can try to take the derivative of cosine. The derivative of cos of x, by this point, it should be almost instinctual. You should look at it and say, is there any way for me to use the original line to solve this particular bit? Well, not really. I don't know the relations between cos and sine quite well enough at this point. Although, once we have implicit differentiation, we will be able to do it. So instead, we just go with the same method of proof. We go to the limit as h goes to 0 of cos of x plus h minus cos of x all over h. And now I'm going to skip steps like crazy. Cos of x plus h, I can expand very quickly. And so I have the limit as h goes to 0 of cos of x times cos of h minus sine x sine h. But already I've got a cos of x. So I'm going to put the minus cos x over here, minus sine of x sine of h, all divided by h. Right? Skip the step, but notice why, notice how, and see if you can justify the way I went from here to here. See if you can fill in the line that I was missing. And so when I take this and I take out a factor of cos of x, I have cos h minus 1 all over h. So I will end up with 0 times cosine of x minus sine h over h will go to 1. So 1 times sine of x. And this is going to give me negative sine of x. So when I take the derivative of sine, I get cosine. When I take the derivative of cosine, I get negative sine. We spend a moment thinking about it. If I took the derivative of that, I would get negative cosine. Derivative of that again brings me right back to sine of x. So what we have, and this is an interesting situation, we begin with f of x is equal to sine of x. F prime of x is cosine of x. The second derivative is negative sine of x. The third derivative is negative cos of x. The fourth derivative is negative sine of x. And so we go right back up to the top. Fourth derivative of x, fifth derivative of x, and so on. We repeat in patterns of 4 over and over. We're going to use that to interesting effect in the examples, and then much more so in the exercises.